Good morning. My name is Paolo Calistri. I'm responsible of the epidemiological unit of the National Reference Center for Veterinary Epidemiology in Italy. And I had the big task to try to give some points in relation to the vector-borne diseases and the use of big data and how big data could be used for the surveillance and prevention of vector-borne diseases. Here we have the contents of my presentation. We will give a rapid look at the past, and then we will try to explore the climatic and man-made factors influencing the occurrence of vector-borne diseases. And then we go to the core of the presentation in relation to the use of big data for modeling, predicting, and early detecting vector-borne diseases. And then the conclusion. As I said, giving a look to the past, we have to consider that in the early 20th century, Sir Ronald Ross was the first one, at least the first to develop a formal mathematical model to try to describe vector-borne diseases, namely the malaria. This was probably one of the first efforts to try to describe in a mathematical way and to analyze all the different forces and drivers influencing the transmission of these vector-borne diseases. In 1964, Gareth Jones proposed the calculation of so-called vectorial capacity, which is an expression for the number of secondary cases that can derive from an infective vector per day in a given place and time. So it gives an estimation of the capacity of spread of a vector-borne disease. If you can see, there is some parameters in the formula that are strictly related to the vectors, such as the daily survival probability of the vector, the extensive incubation periods, that is the time between the pathogen has been taken by the vector and the vector is able to transmit. So the time from which has been ingested the vector, the pathogen by the vector through the blood feed, and the pathogen is able to reinfect the new host because it's ready on the saliva glands. Other aspects are rather the vector competence, so the probability that this specific vector is able to transmit the agent, the pathogen. And other aspects are related to the host. The number of vectors per host, that means that also the host densities in relation to the vector density can play a role. Of course, the climate is something that is influencing the vector-borne diseases. The first evidence is that vector-borne diseases are seasonal. In our latitudes, the vector-borne diseases are mainly during the period of summer and early autumn period, when the temperatures, the temperature conditions are favorable for the mosquitoes. But really, it's not so easy. In the climate is a complex and dynamic system. at the local and the global level, and the effect of the climate on the vector-borne disease transmission is not linear, is not easy and simple to describe, and they can act in opposing direction. For example, just to give a very easy example, just the increase of temperature can increase some aspect related to vector-borne transmission. Some of the parameters that we found in the vectorial capacity formula, such as the vector biting rates or the pathogen replication within the vector body, so reducing the extrinsic incubation period. But on the other side, a higher temperature can decrease the vector survival. So the life of vectors are shorter. And in different situations, that could can result in an increase or in decrease of transmission, depending on the relative effect of these factors. So really is not so easy to correctly represent the effect of the climate on vector-borne diseases. In addition, there are not only climate factors influencing the transmission, occurrence and transmission of vector-borne diseases. We have many other factors, and among them, probably the main factors are those more influencing, more crucial for the occurrence and spread of vector-borne diseases. Here I gave an example of just few man-made drivers that can have a really strong effect in the spread of the vector-borne diseases. Think about, for example, on the changes on the environment with the building of new dams, creating new water pools or lakes or areas that could be favorable for the mosquitoes replication in areas where before those conditions was not present. Think about human mobility, about the possibility of the rapid spread from one continent to the other continent of some diseases, even vector-borne diseases. Think about Zika, think about dengue, think about chikungunya, just through the human travels. And don't forget also the presence of conflicts and wars in many areas of the world, which destroy the health systems, animal health and public health system, thus facilitating the occurrence and spreading of disease and pushing people to migrate. So all these conditions, especially on the short and mid-term, can have a higher effect on the spread of the infectious disease and the vector-borne diseases more than climate. And also at a small scale, at the local scale, or just in our garden, we can have so many different factors influencing the occurrence of small foci of diseases related to the human behavior of the people living in the different areas. So how to catch this complexity? We have so many factors so many drivers mixing together and influencing all together the final outcome that represented by the occurrence and spread of a disease. So how we can try to catch this complexity? Today we have the possibility to use the so-called big data. We have several different kind of big data sources. Here on this slide you can see one of the possible definition of what does it mean big data that's been described by the so-called 3 or 5 or 6 V's. So something that has high volume, high variety, and there's data that is produced on the high velocity. In general, big data is defined as a data set so large or complex that the traditional data processing methods are not useful. And therefore, specific data processing approaches and methods have been developed in the last years and still being developed for manage this kind of big data set. Try to describe how big data and big data sources can be useful and be used and are used for the surveillance, prevention and control of vector-borne diseases. I divide the use of this data in 3 main categories, just to simplify. One, used for modeling the transmission and spread of vector-borne diseases. The other, to predicting the occurrence of the emergency or the re-emergence of the disease in some places or in time. And the last for early detecting the incursion of new or already known vector-borne diseases. Modeling, the use for modeling, some examples. For examples, the use of spatial model. This is the easiest and more known way to try to model the distribution, the spatial distribution or the probability of occurrence in a spatial way for some vector-borne diseases. This is just an example on to predict with the use of some climatic factors like rainfall, like temperature, and also the landscape, if you can say, factors related to the elevation, distance of the rivers, and also host factors, livestock density. So they use all these factors all together to try to define risk maps, in this case for Rift Valley fever, that is mosquitoes-borne zoonosis. For the same disease, Rift Valley fever, the different model for the developing risk maps for each month of the year, in this case in Spain, in case of introduction of Rift Valley fever, which will be the most favorable areas for its spread. Another approach is the use of the mathematical models as the evolution of the old Ross model. That today are more and more complicated, and they try to describe not only the infection and the transmission between vectors and hosts, but also to try to explore the infection through the different vector life stages and so on. What is important here that you can include in this kind of models also control or prevention measures, for example, vaccination, and test the efficacy of the different control measures in relation to reduction on the transmission of the disease. Another approach could be the use of social network analysis. That's something that is being used, especially to try to define the how the disease could spread from one site, from one point to another, and to explore if there is any crucial point, crucial nodes that can super spread the infection to in a relevant way. Has been used for many infectious diseases, for some direct infectious diseases, and this is an example in relation to malaria. To predict the occurrence of the disease. A few examples in relation to that. The most famous use of, in this case, satellite data for the prediction of the occurrence of the a vector-borne disease, namely in this case Rift Valley fever, is the Rift Valley fever monitoring system for East Africa. Periodically, the production of the maps in relation to the risk of occurrence of Rift Valley fever are made by the international agencies, cooperation with MES and other agencies, considering and using satellite data to catch the differences and anomalies in the rainfalls in these areas, because we know, has been demonstrated in East Africa, that anomalies in the rainfall and the effects linked to the so-called Niño phenomenon are strongly influencing the occurrence of some mosquitoes-borne diseases, in particular Rift Valley fever. But for example, this approach that seems to work quite well for East Africa does not work for West Africa. That means that in West Africa, other drivers other than the temperature and rainfall are playing a crucial role, or are playing a role in a different way. Another approach is, in this case, the attempt to integrate not only climate data, but man-made factors, socio-economical factors, production factors, and many others, in try to identify and to predict the possible emergence of zoonotic disease. There are a lot of efforts on that, especially considering the always more frequent emergence of new pathogen in the last period. Finally, the use of the big data for early detecting the emergence of new diseases. This is an example related to Google Trends. This is I just took the computers with the computers the screen when you ask for the Zika virus and Zika fever, and Google Trends is able to look at all the times, the frequencies that specific words has been used in the research into Google in the websites. You can also add the search also in social networks like Facebook and others. As you can see, it's clear, for example, that the peak in the use in the searching in the web of the names related to Zika fever and Zika virus is exactly from the time point of view and from the spatial point of view is overlapping the Zika crisis in South America. The same, this is the screen that you can have with the mobile, and therefore it's in Italian because I made it with my mobile. The same for West Nile, and you can see if you restrict to Italy, the search, that the peak of search of West Nile, that in Italian virus del Nilo occidentale, is from the spatial point of view and from the temporal point of view is the same of the peak of the human cases and infection that we had in 2019 and 2018, sorry, and the same region, the same area affected, more affected by the infection. So the use of this kind of web searching tools can facilitate or can support the possibility to develop disease intelligence monitoring system, for example. At international levels, other systems are available. These are just examples. Try to put together information coming from many different sources, official and not officially, in order to give a quick and an early updated picture of what is happening around the world. So, to conclude, today is clear that several factors, natural like climate, but also man-made, biotic and abiotic, can influence the occurrence and transmission of infectious diseases and in particular vector-borne diseases. Today, the availability of big data that can derive from many different sources is supporting the development of new tools and approaches to better describe, to better define and detect this complexity. Although they are posing new challenges in data mining, analysis, and representation. However, is without any doubt that these new tools and approaches are very useful and in many cases are fundamental for the surveillance of these diseases and for properly predicting and preventing and controlling their spread. Thank you for your attention, and I hope to have given some points useful for further discussion. Thank you.